In this video, we're going to look at another application of work integrals. A spherical tank with radius 2 meters is full of water. Find the work required to pump all the water out of the outlet, which is 1 meters above the top of the spherical tank. Gravity is 9.8 meters per second squared. The density of water is 1,000 kilograms per meter cubed. So to exploit this circular symmetry, we choose the origin to be the center of the spherical tank. We do this to make the integration easier to do. So the height of the vertical circular cross sections of the tank lie between y equals minus 2 and y equals 2, with the outflow pipe at y equals 3, and here's the diagram. Notice that the ground level is at y equals minus 2 and y equals 0 goes right through the center. The x-axis goes right through the center of the sphere. Alright, let's sketch a diagram and define some variables. The most important part of this diagram is this cross-sectional slice and the distance that this cross-sectional slice has to travel to get to the top. So here's a circular cross-section, and we're taking these cross-sections perpendicular to the y-axis. So clearly this is a circular cross-section with radius x. The distance to the x-axis is y. So what is the distance that this slice has to travel to be pumped out of the outflow pipe? That's very important. That's 3 minus y. Why is that? Because 3 is the entire distance here. 1 meter because the outflow pipe is 1 meter above the top of the tank, and radius of the tank is 2 meters. 2 plus 1 is 3. And this distance is y. So the distance from the cross-sectional slice to the outflow pipe is simply 3 minus y. Now this is only one of the slices. There's infinitely many of them. And of course the goal is for us to get the cross-sectional slice as a function of the area, and of course find also the work required to pump one of these slices to the top. But the integral, it's important to realize that the integral takes all of these calculations. The calculations are embedded in the integral. By that I mean that every cross-sectional slice has different area, has different mass, different volume, but the integral basically adds them all up and finds the total work required. We also have these slices below the x-axis, right here. There it is. All right. So now, the key concept is that the spherical tank lies between y equals minus 2 and y equals 2, and every horizontal circular slice at height y has to be raised 3 minus y meters to be pumped out of the outflow pipe. All right, so since the tank is a sphere, all horizontal slices perpendicular to the y-axis are circular disks with radius x meters. Right here, so there is a circular disk with radius x meters. Let's put this in. This is x. This here is the distance from the disk to the origin, and this is the radius of the sphere, which is 2. All right, so cross-sectional slice as a function of y. This is pi times radius squared. The radius is simply x, so we get pi x squared. This is a cross-sectional slice at height y. Now, we need to get this in terms of y, because we're going to add up all these slices in terms of the y direction. The integration is with respect to y. So let's apply Pythagoras to relate x and y. This is a right-angled triangle, so we get x squared plus y squared is equal to radius squared. Radius, of course, is radius of the sphere. So we get x squared, Pythagoras, plus y squared is equal to 4. Solving for x squared, we get x squared is equal to 4 minus y squared. So the cross-sectional slice is going to be pi times x squared, which is equal to 4 minus y squared. This is a cross-sectional slice at height y. Now let's find the differential volume. The differential volume is going to be the cross-sectional slice times dy. Let's draw a diagram. So here is the disk, the radius is x, and dy is the height. So differential volume is pi times radius squared times the height, which is dy. Differential volume is a of y times dy. All right, so we already have found a of y, the cross-sectional slice, as a function of y. So let's substitute that in. We get pi times 4 minus y squared times dy. This is the volume of a thin disk of water. Let's find the mass of this thin slice of water. Well, if we take density of water times the volume, we're going to find the mass. So we have pi times 4 minus y squared times the density of water, which is 1,000 kilograms per meter cubed, times dy. This is a mass of a thin disk of water. All right, so we have differential mass is equal to pi times 4 minus y squared times density, which is 1,000, times dy. This is a mass of disk at height y. Let's find differential force. dF is equal to gravity times mass times the change in mass. So we get pi times 4 minus y squared times 1,000 times 9.8 times gravity times dy. This represents the force needed to overcome gravity acting on a mass of water in this thin circular disk at height y. Let's find differential work. How much work is required to pump this slice over the top? This is going to be work is equal to force times distance. The distance is 3 minus y. This is the distance that the slice has to travel to get to the outflow pipe, times dF. So we get pi times 4 minus y squared times 1,000 times 9.8 times 3 minus y dy. Let's break this down further. So this part is the cross-sectional slice of the disk, A of y, cross-sectional slice, horizontal slice. This part is density of water, rho water. This part is gravity, this is g. And this part is distance. So this dW represents the work required to pump out this thin circular disk of water 3 minus y meters through the outflow pipe. The key concept is that 3 minus y represents the distance that each circular disk of water at height y must travel to be pumped out of the outflow pipe. Let's check it for the ground level and also the top level. If 3 minus y works for the ground level and the top level, it should work for all slices in between. Let's check y equals minus 2. So y equals minus 2. If we go back to the diagram, how much distance does a slice of water at y equals minus 2 have to travel to get to the top? Well, there's 2 meters. This radius plus 2, that's 4, plus 1 is 5. 5 meters. Let's check it. So we have 3 minus y. That's going to give us 3 minus minus 2 is equal to 5. That works out. Now let's check the top. Y equals 2. This is the top of the tank. How much distance does this have to travel? Well, y equals 2 has to travel 1 meter to get to the top. So let's check the calculations. We get 3 minus y is equal to 3 minus 2 is equal to 1. That also checks out. And if 3 minus y works for the top slice of water and the bottom slice of water, it has to work for all slices in between. The integral adds up all the works required to pump out these slices to the top. All right, let's set up a definite integral and find the work required. Differential W, this is the work required to pump out a slice of water to the top, is pi times 4 minus y squared times 1,000 times 9.8 times 3 minus y dy. Now let me repeat this. This is the cross-sectional slice of a disk of water, of a circular disk of water perpendicular to the y-axis. This is A of y. This is density of water. This is gravity. And this is the distance that every slice has to travel to be pumped over the top. All right, so the work done is going to be the integral from y equals minus 2 to y equals 2 dw. This is equal to the integral from minus 2 to 2 pi times 4 minus y squared times 1,000 times 9.8 times 3 minus y dy. Now, this is all constant. Pi is a constant, 1,000 is a constant, 9.8 is a constant. Constants pass right through the integral. So let's simplify our work and push those out of the integral. Pi times 1,000 times 9.8 integral from minus 2 to 2, 4 minus y squared times 3 minus y. Now let's fold this out and simplify it. We get work is equal to pi times 1,000 times 9.8 integral from minus 2 to 2. Opening this up, what do we get? 4 times 3, that's 12, minus 4y, minus 3y squared, and minus y squared times minus y is going to give us plus y cubed. Integration with respect to y. So work is going to be equal to pi times 1000 times 9.8 integral from, let's integrate this. What is the antiderivative of 12? That's 12y. What's the antiderivative of minus 4y? That's 4y squared. Reversing the power rule, divide by 2. And then here we get minus 3y cubed, divide by 3. Reversing the power rule again. And the integral of y cubed is going to be y to the 4. Add 1 to the exponent, divide by the same. Evaluate it from minus 2 to 2. All right, so what we have is work is pi times 1000 times 9.8. And if we simplify this, apply fundamental theorem of calculus, plug 2 in, and plug negative 2 in. Actually, let's show that work. Work is pi times 1000 times 9.8 times 12 times 2 is 24. Minus 2 squared is 4 times 2 is minus 8. And then this 3 cancels out. Minus 8 plus 2 to the 4th is 16 over 4 is 4. Minus, now put a lower limit in, we get minus 24. We get minus 2 squared is 4, that's minus 8. And minus 2 cubed is minus 8 times minus is plus 8. And we get minus 2 to the 4th, that's plus 16 over 4 is 4. If we simplify all of this, we're going to get pi times 1000 times 9.8 times 24 minus 8 plus 4 plus 24 minus 4. And all of this works out to 32 if we plug this into a calculator, or if we do it mentally, pi times 1000 times 9.8 times 32. And multiply these numbers, we get 313,600 pi joules. If we decimalize this, we're going to get, the work is approximately 985203.46. So that's 985,203.46 joules required to pump all the water over the top. All right, thank you.